Assalamu alaikum. In this video, we'll discuss physics, chapter 10, section 3, the second law of thermodynamics. Objectives of our lesson: recognize why the second law of thermodynamics requires two bodies at different temperature for work to be done. Calculate the efficiency of the heat engine and relate the disorder of a system to its ability to do work or transfer energy as heat. Efficiency of a heat engine. The heat engine is a tool used to convert heat into work. It takes in heat and converts it into work. By taking a heat from a hot reservoir and doing work, and heat is transferred to the cold reservoir. The difference between the heat taken from the hot reservoir and the heat given to the cold reservoir equals the net heat or equals to the net work done. So as seen in the last section, that the work or the net work equals Q net, or the difference between the heat given by the hot reservoir and the heat given to the cold reservoir, QH minus QC. QH here means hot reservoir, and QC the heat given to the cold reservoir. So H stands for hot and C stands for cold. According to the second law of thermodynamics, work can never be equal to QH in a cyclic process. Can we neglect QC, or QC can be equal to 0? It can't. So there should be heat given to the cold reservoir. So in other words, some energy must always be transferred as heat to the system surrounding, or QC must greater than 0. QC is equal to 0 never happen. The second law of thermodynamics can be stated as follows: no cyclic process that converts heat entirely into work is possible. So the work, the heat, the total heat taken from the hot reservoir cannot be transferred totally to work. Some heat should be taken to the cold reservoir. A measure of how well an engine operates is given by the efficiency. So the efficiency measures how well an engine operates, and it gives the ratio between the energy out and the energy in. The ratio between the energy out and the energy in. So in general efficiency, a measure of useful energy taken out relative to the total energy that put into the process. So efficiency equals energy taken, or energy, useful energy to the work, and the total energy that put into the system equals QH. And we know that the net work equals QH minus QC over QH. So QH over QH equals 1 minus QC over QH. So this is the efficiency of a heat engine. So the efficiency of the heat engine equals the net work divided by QH, or QH minus QC divided by QH, which is equal to 1 over QH over QC, QC over QH. Note that the efficiency is unitless, no unit. It has no unit because it's a ratio between two quantities, two identical quantities, which are energies. Because of the second law of thermodynamics, the efficiency of a real engine is always less than 1. Because if QC equal to 0, the efficiency equals 1 or 100%. But QC greater than 0. So the efficiency less than 1 or less than 100%. Example. Find the efficiency of a gasoline engine that during one cycle receives 204 joule of energy from the combustion and loses 153 joule as heat to the exhaust. Here is the cylinder of the gasoline engine in which the gasoline is burned to produce 204 joules. This heat is converted into work and a part is lost to the surrounding 153 joule QC. QH equal 204. So the given is QH equal 204 and the QC equals 153. The unknown is the efficiency. Okay. To calculate, substitute in the equation. Efficiency equals 1 minus QC over QH equals 1 minus QC equals 153 joules and QH equal 204 joules. Calculating, so the efficiency equals 0.25 and this efficiency equal 25%. So only 25% of the energy added as heat is used by the engine to do work. Only 25% is converted into work. And the 75% is lost as heat to the surrounding air. So the efficiency is less than 1. Entropy. What's entropy? In thermodynamics, if you leave a system, the system is left to itself, it tends to go from a state with a very ordered set of energy to one in which there is less order. Like the students in the classroom, they are ordered, arranged. While if you leave them to go to the playground, they start to become disordered. Inside the classroom, they are ordered. They are under control. If you leave them, they start to be disordered. Okay, in the playground, for example. So, in thermodynamics, a system left to itself tends to go from a state with a very ordered set of energies to one in which there is less order. From high order to less order. The measure of a system disorder or randomness is called entropy of the system. The greater the entropy of a system is, the greater the system disorder. So entropy means disorder or randomness. More disorder, more entropy. More randomness, more entropy. Less randomness, okay, less entropy. Less disorder or more ordered is less entropy. Okay? So entropy is a measure of the disorder or randomness. Entropy, disorder or randomness. The greater probability of a disordered arrangement indicates that an ordered system is likely to become disordered. The greater probability of a disordered arrangement indicates that an ordered system is likely to become disordered. The ordered system changes to disordered system. Put another way, the entropy of a system tends to increase. The entropy always tends to increase. Means what? It is change from ordered to disorder. So the entropy of a system tends to what? To increase. Greater disorder means there is less energy to do work. So for the system to do homework, it's needed to be more ordered or less disorder or less entropy. If the gas particles move to the piston, as you can see in the figure, all the particles are moving toward the piston. So they are ordered. They have less entropy. So all the particles here are moving towards the piston. All of the internal energy could be used to do work. But this is not the case. Here, well-ordered, high efficiency, and high improbable distribution of velocity. While in the second figure, highly disordered, average efficiency or less efficiency, and highly probable distribution of velocities. So this extremely well disordered system is highly improbable. Okay, so more entropy, less energy can be extracted, or less energy can be converted into work. While less entropy, more ordered, means that more energy can be converted into work. Because of the connection between systems entropy and its ability to do work and the direction of energy transfer, so the second law of thermodynamics can be expressed in terms of entropy changes. What that? The entropy of the universe increases in all natural processes. The entropy of the universe means that the universe becomes more disordered. The entropy of the universe always increases. Pay attention. The entropy of the universe always increases all natural processes. Entropy can be decreased for parts of a system, provided this decrease is offset by a greater increase in entropy elsewhere in the universe. For example, if the entropy decreases in a certain part of the universe, it will increase in another part, in another region, elsewhere. So, if the entropy can be decreased in a part of the universe, it will increase in other parts by a greater amount. Pay attention. For the total entropy to increase. Let's discuss an example of the change of entropy. Energy change produced by refrigerator freezing water. Here in the figure, in the left figure, inside the refrigerator, the water temperature decreases and it changes into ice. So the particles of water become more ordered. More ordered means less entropy. So the entropy here decreases. Inside the refrigerator, the entropy decreases. Outside the refrigerator, the temperature of the outside of the refrigerator increases and the particles of air becomes hot, so they move faster and they become less ordered or more disordered. So the entropy outside the refrigerator increases. So inside the refrigerator, entropy decreases, and outside the entropy increases. So, but not by the same amount. The increase here larger than the decrease here. If the increase equals 12 and the decrease equals 10, so the difference will be to increase. So because of the refrigerator's less than perfect efficiency, the entropy of the outside air particles or air molecules increases more than the entropy of the freezing water decreases. Okay, so the total entropy will increase. This is the second law of thermodynamics, or the law of entropy.